Hello, we're back with another video, this time talking about radiation units, again specific to radiography. And if you haven't watched one of these videos before, my name is Alex. I'm an instructor for radiography, specifically limited radiography, at Central California School of Continuing Education on the Central Coast in California. And I do these review videos after each class so that my students can hopefully go back and look at the terms and information that we looked at during the lecture and sort of bring it all together. This talk is about radiation units, specifically the SI units of radiation that we use and that will be tested on when we take our state and national registry exams. So the concept of measurement. So in science and medicine, radiation units from the SI system are now the worldwide standard. SI stands for Systeme International. If you have been a radiographer for a while or have talked to older radiographers like myself, you will no doubt heard of the British system of measure, which uses things like the rad and the rem and the Röntgen, which are older units of measure. Nowadays we use the SI system that basically is just a more widely accepted unit of measure, system of measure in radiography. So 4 types of quantities that need to be measured: radiation exposure, radiation dose, dose equivalent, and effective dose. So exposure, narrowly defined as the intensity of radiation incident upon the surface of an object. Best detected as ionization events in the air just above the surface of an object, which generate electrical charge in the detecting device. So to measure exposure, we don't measure anything after it has struck the surface of the object. We're measuring ionization events in the air. If you've watched some of the previous videos, you've learned the term ionization. Ionization is the creation of a charged particle when an electron in an atom is given an increase in energy. For example, when it absorbs a photon of electromagnetic radiation, the electron can be liberated from the atom, and that creates an ion pair where you leave behind an atom with a net charge of +1 and an electron that has a net charge of -1. Those charged particles can interact with other particles and cause issues, for example, in our DNA. So in any case, we're trying to measure ionization events in the air above the surface of the object. We call this entrance skin exposure. It's the intensity of radiation entering through the surface into the body, not the amount absorbed by the body. You may have heard like our atoms are mostly empty space. That's true and not true, but at least for this talk, we can call it true. And atoms are made of charged particles, protons and electrons. I didn't mention neutrons on purpose, but anyways, atoms are made of charged particles, whereas electromagnetic radiation, the stuff that we're making, the X-rays that we're making, don't interact with charged particles because they don't have a charge. They don't interact directly by they just don't have a charge, so they're not going to be attracted to or pushed away from electrons or protons. So a good amount of X-rays pass right through the body without interacting with the body. So the measure here of entrance skin exposure is again a measurement of what is above the intensity of radiation above the surface of the object, not what has been absorbed by the body. Okay. So we speak of being exposed to things from the outside. It is interesting to know that we are always, anything that is matter is always radiating energy in the form, for example, in the forms of infrared radiation, because all of our atoms are always in a state of motion. So we're being exposed internally to radiation. That's not really what we're talking about. That's inherent, that's part of us. We're talking here about being exposed to something from outside the body. That's radiation exposure. Radiation exposure, again, is narrowly defined as the intensity of radiation incident upon the surface of a body. be it a human body or an ion chamber. And again, the only way to count X-ray photons before some of them are absorbed by an object is measuring the ionization events that are caused in the air above the object and sort of extrapolating from that how many X-rays, or more correctly, the intensity of the exposure. Electrons liberated from air molecules can be attracted to the positive anode of a detection device, where they generate a small electric current that can be measured by an ammeter. An ammeter measures electric current, or stored as electric charge in a capacitor to be read later. All right, our unit for exposure, Coulomb per kilogram. It's a direct measure of electrical charge generated in air, and roughly speaking, about 6.3 billion ionizations in 1 meter cubed. At typical atmospheric pressure, a cubic meter of air weighs about 1 kilogram. For those of us in the United States, almost all of us I would assume, 1 kilogram comes out to about 2.2 pounds. Kilogram is a unit of mass that we use as to describe weight, whereas the pound is just a unit of weight. We like units of mass when we use the metric system and the Systeme International. So Coulomb per kilogram is 6.3 times 10 to the 18th liberated electrons in 1 cubic meter of air. If you can do that, if you can liberate 6 billion electrons in 1 cubic meter of airspace, we're going to call that 1 Coulomb per kilogram of exposure. Air Kerma. The quantity of air Kerma has largely replaced the quantity exposure for expressing the intensity of the raw X-ray beam. We would call this like the primary beam, emitted by the X-ray tube at a particular distance, or the concentration of X-rays at the body's surface. Air Kerma uses the unit gray, capital G, lowercase y for abbreviations. We're going to talk about it in just a second. This unit, though, applies to absorbed energy rather than electrical charge generated. Absorbed dose. As I talked about just a few minutes ago, X-rays are electromagnetic radiation, and they are not charged. They don't carry a plus or minus charge. So they're not necessarily attracted to protons or neutrons in the way that electrons would be attracted to protons, or protons attracted to electrons. So since some X-rays penetrate all the way through the body without interacting with the tissue atoms, we cannot base biological damage simply on exposure, because you can say you were exposed to this much, but we can't say how much of that then was absorbed by the body. So absorbed dose is a better unit for saying how much was, and for lack of better terms, how much was absorbed by the body. So like a dose of medicine is internalized into body tissues, a dose of radiation implies internalized energy, whereas exposure simply connotes only what we were exposed to from the outside, as in externally. So for a better idea of how much the body actually took in and internalized, we have to use a unit of absorbed dose. The unit for measuring the concentration of radiant energy actually deposited within a specific body tissue in SI units is the gray, GY. The gray is a big unit. For reference, 1 gray to the whole body is enough to kill a person. The better way to say it is, no one really has been documented to die under being exposed to under 1 gray to the entire body in an acute dose. People have been documented to die after being exposed to 1 gray to the entire body as an acute single dose. So 1 gray is a lot of energy, a lot of electromagnetic energy. So more commonly for regular exposures, we use things like the milligray, which is 1/1000th of a gray, and the microgray, 1/1,000,000th of a gray. Those are more commonly used for radiography purposes. For absorbed dose, the gray is defined as 1 joule of energy deposited per kilogram of tissue. 1 joule is enough energy to push 1 amp of electrons of electrical current through 1 ohm of resistance for 1 second. That's the joule. So the gray is 1 joule of energy deposited per kilogram of tissue. 1 gray equals 1 joule per kilogram. The gray is our unit. Kerma was mentioned, air Kerma was mentioned a little bit ago. Kerma actually stands for something: kinetic energy released per mass. We have 2 units for the gray. We want to know about the gray of the air, the absorbed dose in the air, okay, or the absorbed dose for the tissue. So gray subscript of A, capital A, denotes energy absorbed in air. This is air Kerma. Gray subscript T denotes energy absorbed in tissue. If we don't specify, if you see a unit posted, for example, you know, you've got 1 gray listed here. If I don't tell you it's tissue or air gray, you assume it's tissue. It's implied that we're talking about tissue, not air. But if we give you the subunit, then you can go off of that. We can be explicit about it. Gray air or gray of tissue. If we don't say, it's just gray of tissue. All right. When using the unit gray, the term entrance skin dose is technically more accurate than the term entrance skin exposure, because the unit describes absorbed energy just over the surface of the body. However, in practice, entrance skin dose and entrance skin exposure have become interchangeable when using the unit gray to describe radiation exposure at the surface of the body. I'll tell you why in just a sec. 1 gray of air Kerma and 1 gray of tissue Kerma are both defined as 1 joule per kilogram, and a kilogram of air has the same mass as a kilogram of body tissue. The distinction between the two is not the mass, but the volume being implied. So visualizing volumes, we said 1 cubic meter of air has a mass of 1 kilogram. As for average body tissue, 1 kilogram of mass is given by a 10 centimeter cube. So shown on this image is a 1 meter cube and a 10 centimeter cube. Both, if given 1 gray, would be the same amount of exposure or absorbed dose into those areas. It's just the volume changes, whether it's air or tissue. It's still the same amount of mass though. Okay. So 1 cubic meter of air has a mass of 1.23 kilograms. For our intents and purposes, we just say 1 kilogram. And a 10 centimeter cube of soft tissue has a mass of 1.24 kilograms, which is about a perfect match. So a 10 centimeter cube of soft tissue has a mass of 1 kilogram roughly, and a 1 meter cube of air has a mass of 1 kilogram roughly. Therefore, we can state that 1 gray delivered to a square meter of air will deliver 1 gray to each 10 centimeter cube of tissue within the body, each cube about the thickness of the lower leg. Body tissue is approximately 1,000 times denser than air. Because some radiation penetrates through the body, the absorbed dose is expected to be slightly less than the surface exposure. Accurate measurements show that in general terms, 1 gray of air Kerma, 1 gray sub A, is equivalent to about 0.96 grays of tissue dose. Because they're so close, and because we need to really focus more on the theory rather than the exact numbers, we just round up and we say 1 gray of air Kerma results in approximately 1 gray of tissue dose. All right, the dose area product. So this is talking more about actual biological damage. Harm to the organism is greater when a larger area of the body is exposed to radiation. This means that we must take into account the collimated field when we consider dose. This is the dose area product. It's simply the dose multiplied by the field size area. For example, You take an 18 by 24 collimated field or a 24 by 30 collimated field and give both of those collimated fields a dose of 3 microgray. Every 10 centimeter cube that can fit into that body, that collimated field, will receive 3 microgray. Since the unit of exposure is joules per kilogram, the unit of absorbed dose, the gray, is 1 joule per kilogram. The gray dose and the field area are almost independent of each other, in that as you increase the field area, every kilogram of body tissue is going to receive 3 micrograys, in this case, of absorbed dose. This is the reason why it's so important to minimize our collimated fields in radiography, and we just say it to minimize exposure to the patient. Well, this is the reason why. The larger the collimated area, the more tissue irradiated equates to an increase in exposure in joules per kilogram. So an example, the dose area product for patient A, he gets 3 microgray times 18 centimeters by 24 centimeters, which is equivalent to 3 by 432 centimeters squared, multiplied out, 1296 microgray per centimeter squared. Patient B receives the same dose, but to a larger area. So 3 microgray to a field of 24 by 30 centimeters. Multiplied out, we get 2,160 microgray per centimeter squared. We just see right there that patient B receives more absorbed dose because a larger area was irradiated. Quick math on it, quick division, and we see that patient B receives 67% more absorbed dose, or roughly 2/3 more harm than patient A, simply because of a larger area, not an increase in exposure, not an increase in dose, just a larger area. Dose area product is similar to exposure area product, but dose area product is more practical for monitoring radiation, so for that reason we primarily talk about dose area product rather than exposure area product. It measures actual energy absorbed. Radiographic and fluoroscopic units can be equipped with dose area product meters or with computer programs that can just simply calculate dose area product for each exposure. Okay, next up, dose equivalent. The gray, technically a physics unit. We talk about the gray in regards to absorbed dose. We usually use the gray when we're talking about our patient's dose. When we're going to talk about how much harm the exposure creates, we need to use a different unit. We need to take into account something else here. Our unit is the sievert, capital S, lowercase v. We derive sievert from gray by multiplying something called the radiation weighting factor, W sub R. That is, we're comparing the harmfulness of a type of radiation compared to X-rays, specifically compared to 200 kilovolt X-rays, so that we have kind of a standard to go off of. So our radiation weighting factors, X and gamma rays get a radiation weighting factor of 1, beta emissions and positron emissions have radiation weighting factor of 1, fast neutrons anywhere from 5 to 20 depending on velocity, and roughly averaged out at 10. And alpha particles being so massive, alpha particles are a helium nucleus, being so massive and being charged, their radiation weighting factor is extremely high. Alpha particles would be considered to be a high linear energy transfer type of radiation, whereas X-rays are low linear energy transfer, or LET. In another video, I'll talk about LET. So the question here, how much harm is done by a 4 milligray dose of alpha particles? Well, simple answer, take 4 milligrays, that's your dose, multiply it by the radiation weighting factor, and you get a dose equivalent of 80 millisieverts. The harm done by alpha particles is 20 times more harmful to biologic organisms than the harm done from X-rays. So we primarily just really are concerned with X-rays. So because the radiation weighting factor for X-rays is 1, the relationship between exposure, dose, and dose equivalent is super simple. 1 gray of air Kerma, 1 gray sub A, equals 1 gray sub T, equals 1 sievert. They're all roughly equal to each other. But again, if we want to be super technical about it, 1 gray of air Kerma delivers about 0.96 tissue dose of gray, equating to about 0.96 sieverts of dose equivalent. So, effective dose. Effective dose is adding in a tissue weighting factor to tell me how harmful this radiation is to a specific body tissue. So not taking into account the radiation type, just changing the tissue types now. The tissue weighting factor is a capital W subscript T. To calculate effective dose to an organ, the dose is multiplied by the tissue weighting factor, the relative sensitivity of the exposed tissue compared to other tissues, and our numbers here. Cortical bone, the cortex of the bone and skin, 0.01. Organs in general, 0.05. Bone marrow, colon, lung, stomach, 0.12. The breast, 0.05, and the gonads, 0.2. The higher the number, the more susceptible to harm the type of tissue is. The gonads being a highly mitotic body tissue, especially in males, always producing more sperm, and in females always developing an ovum. Those tissues, the gonads, are extremely sensitive to radiation damage, whereas your nervous system, for example, or in the cases of things on the screen, your cortical bone is less mitotic than your bone marrow. Bone marrow is 12 times more sensitive to radiation damage than cortical bone. So we use this tissue weighting factor to kind of add in how susceptible to harm the body tissue is when exposed to this, when given this much of a dose. So question: how much harm is done by a 600 microgray dose of X-rays to the gonads? Take 600 microgray, multiply it by 0.2, and that tells you what's called the effective dose. 120 micrograys of effective dose is the answer there. Okay, so the proper use of the units. And to sum it all up, the coulomb per kilogram is a physics unit appropriate for describing the X-ray beam as it leaves the X-ray tube. The gray is also a physics unit. It can be used to describe air Kerma or tissue Kerma. Simply tell me, are you talking about the air or are you talking about the tissue? Remember, 1 kilogram of mass in air is about 1 meter cubed. 1 kilogram of mass in tissue is about 10 centimeters cubed. And the gray is defined as 1 joule per kilogram. The sievert is a biological unit for expressing the dose equivalent or effective dose. Simply calculate with the gray and the radiation weighting factor for dose equivalent multiplied by the radiation weighting factor. Or if you want to figure out effective dose, calculate the gray multiplied by the tissue weighting factor. Okay, so those are our main units for radiation measurement in radiography since 2018, since the ARRT implemented the SI units of measurement and have now made that the standard. However, personnel monitoring companies continue to use the older unit, millirem. REM stood for Röntgen Exposed Man. The REM is kind of like the sievert in SI units, and it describes the describes the absorbed dose of radiation multiplied by the same tissue weighting factors and so forth to give us the REM. And because the REM is still a pretty big unit, we would commonly use the millirem. For perspective, 1 gray and 1 sievert is equal to either 1 100 rem or 100 rad, depending on which of the two units you're talking about. If you need to convert back and forth between millirem and sieverts, it would be best to convert between millirem and microsieverts. So you multiply 1 millirem, for every 1 millirem, multiply that by 10 microsieverts, and that gives you your conversion factor for going back and forth between SI units and the conventional British units. And last couple notes here. We don't deal with radioactivity as a limited radiographer, but nuclear medicine radiographers do. So we should understand that we, as limited radiographers, are using a type of energy called electromagnetic energy. Nuclear medicine radiographers use different types of energy. They use radioactive particles. They use massive radioactive particles that have charge and are spontaneously radioactive. They emit parts of themselves. Those are the alpha and beta and positron and neutron emissions that I mentioned a little bit ago. The unit for radioactivity, though, is the becquerel. It's defined as 1 single decay event per second. So a rate of 1 becquerel is 1 decay event per second. A decay event can be the emission of any electromagnetic wave or any particle from an unstable radioactive sample. In this case, the electromagnetic wave would be a gamma ray, and it would be a energy emission from the nucleus of an atom. Whereas X-rays are emissions from the orbital electrons around an atom, this type of emission would be, again, from the nucleus, and any particle emitted from an atom is coming from the nucleus, specifically the nuclei of unstable radioactive samples. And collective effective dose is the sum of individual effective doses for an entire population. And lastly, a table summarizing all of these units. So the basic standard international radiation units summarized to finish this up. The gray is a measurement of air Kerma, or exposure. It's defined as energy absorbed in air, or joules per kilogram, abbreviated gray, or gray sub A. The next is still the gray, but different gray this time. The gray of tissue dose, energy absorbed in tissue, still in units of joules per kilogram and still abbreviated gray. More specifically, this would be gray sub T. The sievert, dose equivalent. It's a unit of biologic harm. We abbreviate it capital S, lowercase v. We like the sievert when we talk about radiographers' dose. So when we talk about dose to a radiographer, we use the sievert. When we talk about dose to a patient, we typically use the gray. And lastly, the becquerel, a unit of radioactivity. And this is describing decay events per second. 1 becquerel is 1 decay event per second. The abbreviation there, capital B, lowercase q. And that completes the lecture on basic radiation units, the SI units of measure. Thank you.